Hello dear friends, I welcome you to the next video of my series Energy and Climate with the sub-series Plan B for the climate. And what Plan B is, I explained in many videos before. But of course, all these videos I did before were in German because my YouTube channel is basically a German language channel. And this is the first video I do in English. And the reason why I do it in English is because the things I'm going to tell you might be interesting although for people in the US or in England or in Australia or somewhere where the people speak English. That's the reason. So it's my first attempt, and I'm sorry my English might not be that good because I'm kind of out of exercise. I need more exercise in English. And my friends in the US, they tell me I'm not speaking English, I speak Germish. So there might be a German accent, but I hope you will be able to understand what I'm telling you despite my accent. So what is the title of my video here? It's Professor Happers, William Happers' thesis. So William Happer is a professor at Princeton, and he has certain ideas about climate warming. And many of my watchers and listeners or subscribers, they ask me, can you make a video on the ideas of Professor William Happer? And that's the reason why I read through several publications from William Happer, and I had some comments on that and some analysis, and this is what I want to tell you in this video. So that's the idea, Professor Happer's thesis. And first, before we start with the video, I would like to explain to the new listeners from the English-speaking ones here, who I am. I'm a professor for experimental physics, and I'm retired since 1.5 years. And I worked for 25 years at the University of Constance at Lake Constance in South Germany, and I did my research and a lot of teaching in nanoscience. So this my basic field of research is nanoscience, but I did a lot of teaching covering the whole of physics, because teaching need to be not only in what I do my research on, but it need to be in all fields of physics. Yeah, so I did lectures on energy, climate, astrophysics, and quantum physics. Especially on energy and climate, I had several courses for a full semester, so it's 3 or 4 months of lectures on energy and climate. And some of this is on my YouTube channel, and I think it's altogether it's 45 or 44 hours of lecture. So it's a lot of knowledge on nuclear physics, nuclear reactors, on solar energy, wind energy, geothermal energy, and of course all the things with the climate. So the greenhouse effect and the greenhouse gases and so on. It's a lot of knowledge. And this is the reason why I also, the people ask me whether I can explain some certain problems of climate and energy, and one of these problems are the ideas of Professor William Happer. Okay, so that's the idea of this video. Some more background. Today I have a little consulting company. It's called, this is that's a homepage, 4psciencelab.com. I have the YouTube channel. It's basically German. I'm sorry. Grenzen des Wissens, which means in English limits of knowledge, and it's all on physics. And I'm a speaker. I give public talks, and that's my homepage here, www.gantefer.ch. And I wrote a few popular science books. So that's me. And that's the reason why people ask me to make an analysis of Professor Happer's statements, because, well, they tell me I have the talent to explain physics to just a regular citizen. Yeah, that's what I try to do. And first, also, before we start with the main content, my position in the debate on climate and energy. And I think there's this scale here between the climate activists and the climate skeptics. So the activists, they claim we need to do immediately something, we need to decarbonize, get out of fossil fuels, stop using coal, oil and gas, otherwise we will, and some of the extreme activists say that we will die out. Yeah, so that's one end of the scale. The other end is, well, first there are the deniers. They say well, we don't have a climate warming due to the human activities. There might be a warming, but it's caused caused by the sun or something. Then we have others who say, well, there is a climate warming. It might be caused by the use of fossil fuels, but it's not so bad. And this is exactly William Happer. He says, we will see that, he says it's not that bad. We might just continue to use fossil fuels and live like we did for many decades now, because the climate warming it's happening, yes, but it's not so bad. So this is the other end of the scale. And I try to be in the middle and keep to the physics. I try to understand the underlying physics and explain this to the people who have no background or almost no background in physics. That's the idea of all these videos on my channel, yeah. And but I must just tell at the very beginning, I'm in 90%, not 100%, but almost 100%, 90% agreement with the IPCC. This is the International Panel on Climate Change. So this is all the climate researchers. I'm in agreement with them, especially with the working group 1. These are the scientists. The other working groups are other people. And I refer especially to the newest big report of the IPCC, is the assessment report number 6. So most of this, what you find from the working group 1 in this assessment report number 6, I agree with. And I have read it, and I think most of it I did understand. So from this perspective, we try to analyze the statements from Professor William Happer. Yeah, and also just before we start with the content of the video, I would make another statement from myself. I do understand the people who follow people from the skeptic sides, who tell the people, oh yeah, we can continue to drive cars and to eat schnitzels and steaks and so on. I do understand these people, because I myself, I feel the same, yeah. I'm kind of tired of all the bans, restrictions, regulations, price increases, and the bureaucracy caused by climate action, yeah. So politics put a lot of pressure on all the citizens in, at least also here in Switzerland, in Germany, in Austria, and also in the US and many other states, a lot of pressure, so that we, yeah, it's kind of pain in the, well, yeah, it's a pain, yeah, that we have to obey new rules, because we need to reduce the CO2 emissions. And I can understand that we get tired of this. Yeah, it's bans of gas and oil heatings, at least in Germany, that's a big discussion. Combustion cars, and then schnitzel and French fries. That's my favorite dish. Yeah, and if it comes to that, with the climate action, that we all need to go vegan. Yeah, then I must say I quit. Yeah, I don't do that, because it's my favorite dish. I want my schnitzel with French fries and the German sausage. Yeah, I don't want to have anybody controlling what I'm eating and what I'm not eating. Yeah, many other things, yeah, like the combustion cars. Okay, we can drive maybe with electric cars, but not too much. Yeah, but I do understand the many people, the many citizens in the many states who get tired of all these climate regulations. But, and there's a big but, we still need to keep to physics. We cannot deny physics because we are tired of these regulations. So sorry about this. So we need to analyze the statements from Professor Happer from the point of view of physics. And I try my best to explain this to you. Yeah, who is Professor William Happer? He is an American physicist. So this is from his Wikipedia homepage. American physicist. He worked on atomic physics, optics, and spectroscopy. And I did also a lot of spectroscopy on nanoparticles with lasers. So I'm also a spectroscopist. So he's a colleague of mine. And he's also an emeritus, like myself. And he worked at Princeton University. Yeah, Princeton. Princeton is one of the most famous places in the world you can do research. So whatever a professor from Princeton tells you, you should listen to that. He is a bright guy because he is at Princeton. Yeah, so we need to be very careful with his arguments. And in addition to that, being a professor at Princeton, he also climbed up the ladder in the political system because he was in the Jason Advisory Group, which is an advisory committee advising the administration in Washington, so the US government. And he was for a few years director in the Department of the Energy's Office of Science as part of the George W. Bush administration. So that's a few years ago. So he was way up in politics too, beside his high position in research. And here's one of his statements, just to start with, to make clear what his position is. Science demonstrates, that's what Professor Happers says, science demonstrates there is no climate-related risk caused by fossil fuels and CO2. So he thinks, yes, it might get warmer and there might be some changes of climate caused by the fossil fuels and CO2 emissions, but they are not that bad. We can simply continue. So that's his position. Yeah, well, you can simply say that's nonsense, but he has arguments to confirm his statement, and we need to analyze his arguments, and that is what I will do in this video. But before we do that, I need to thank all the people who support our channel. So to make these videos possible, we of course need a little bit of money, and many people, well, not many, unfortunately, but some people support us with small amounts of money. And I need to say thank you to all these people. Without you supporters, there would be no YouTube channel. Yeah? And there are two possible ways to support us. One is via PayPal via one of these two email addresses, or we have two accounts. They are both located at a Swiss bank because I'm living in Switzerland and my company is in Switzerland. And also the YouTube channel is located in Switzerland. So it's a Swiss bank, but the two IBAN numbers we have here, one is in euro and the other one is in Swiss francs. So we would be very happy if you could support us with just a small amount of money with our attempts to bring more reason into this climate debate. So thank you very much to all of you. And now we start with the content of the video. And I refer only to one paper from Professor Happers, and this is this one here. And it's a PDF everybody can download here. Here's a link to download this paper. It's something like 20 or 30 pages. And he has written this together with Richard Linssen. So there are two authors. And Richard Linssen is also an emeritus professor of Earth, Atmospheric and Planetary Sciences from the MIT, Massachusetts Institute of Technology. And it's just one of the many papers from William Happers and many of his publications. Also, there are videos. They contain his main arguments. And this is just selections. I use this paper. I could have used any other paper where I can find his main arguments. Yeah. And this paper is a comment and declaration on the SEC's proposed rule and so on. So it's a rule for investors. But it doesn't matter what it is because it contains his main arguments. And so this is a paper, and I withdrew several of his arguments from this paper here. And we start with two statements the two authors of this paper made at the very beginning of this paper. And the first is from Richard Feynman. It's a citation. And Richard Feynman, he's a very famous physicist. He said, we compare the result of a theory's computation. Well, this refers, of course, in this content here, it refers to the climate model. A theory's computation to nature, compared directly with observation to see if it works. If it disagrees with the experiment, it is wrong. In that simple statement is the key to science, says Professor Richard Feynman. It's quite a while ago. Well, here, 1965, he said that. And that's the idea of natural science. You have experiments, you have theory. And only if they fit together, it's real science. And the problem with climate model predictions is that we have no experiments. There's a prediction what might happen to the climate in 15 years, 50 years, or in 100 years. And we have no way to falsify that. Yeah, we can just believe it, whatever the climate model scientists tell us. Yeah, so there's no way to prove it. So there's no experiments, and that that means it's not real natural science. Yeah, sorry about that to all the people who do this climate modeling, but well, yeah, but we need a proof by experiments, and we don't have that in this case. So that is a big disadvantage of climate models. And I even follow Karl Popper. He's an Austrian and British philosopher, a science philosopher, and he says a science theory must be falsifiable. If it's not, if you cannot prove it's wrong, then it's not a science theory. Yeah, so that's it. So I agree with this introductory statement from Professor Linson and Professor William Happer, yes. And there's another statement in the beginning of this paper, also referring to Richard Feynman. No government has the right to decide on the truth of scientific principles. And this refers to the influence of politics on the big reports of the IPCC. And I learned, I'm not sure whether it's true, but I learned that the summaries for policymakers of these big reports, so there are these big reports of the IPCC, it's several hundreds or even thousands of pages, and there are summaries. And these summaries, they summarize the content of the science. However, I'm not sure whether it's true, but I heard that these summaries are written by politicians, so some people who work for the governments and not the scientists themselves. Yeah, but then it's, again, not real science, because science needs to be independent of politics. Yeah, if it's true, I'm not sure. But I read always these several hundreds or thousand pages. I only read the original work from the scientists. This is what I'm interested in. Okay, these two statements from Richard Feynman, which Professor Happer put at the very beginning of this paper, I totally agree with. Okay, and now we come to the part where I don't agree anymore with Professor Happer. And this is this statement here. And it says, our informed scientific opinion of these two authors of the paper is that doubling CO2 concentration will cause about 1 degree Celsius or less warming. So he says that the climate sensitivity, this is this doubling thing, the climate sensitivity is only 1 degree Celsius. I don't know, there's something like 2 degrees Fahrenheit or less, yeah. So that would be a very small amount of warming. Yeah, climate sensitivity is defined as doubling the concentration of CO2 with respect to the concentration we had before the Industrial Revolution, so something like 1800 or so. There we had 260 or I think 280 parts per million. So CO2 is, of course, only present in the atmosphere with a very low concentration. It's a spurious gas. So 280 parts per million. Today we have 420 parts per million, and the doubling would be 560 parts per million. And the people calculate the warming if we have a doubling of the original concentration from 280 to 560 parts per million. And Professor Happer claims it's only 1 degree of warming. Yeah, that's not much, I would say, because it means this warming is not bad. Yeah, it's low, so we don't have to be worried about it. But I think he made a mistake with this very small thing, because he calculated only the direct response of the system. So what does a greenhouse gas do? It blocks partially the infrared radiation from the surface of the Earth into the empty space, a cold space. So this is a cooling mechanism. And so the greenhouse gases block part of this infrared radiation. And if we double the concentration of CO2, of course, the blocking gets worse. So it's more blocked. So it gets hotter on the surface. So that's the idea. And he says it's only 1 degree. Yeah, that is the direct response. But there are some feedback processes which amplify the direct warming processes. And it's a positive feedback, self-amplifying. And there are two main effects. And I think Professor Happer neglected these effects. And one effect is the water vapor. If it gets warmer only by 1 degree first, yeah, then more water vapor will be coming out of the warmer ocean. So more water vapor is vaporized out of the oceans. So the water vapor in the air increases a little bit. But water vapor is also a greenhouse gas, so this amplifies the greenhouse effect, and the infrared radiation gets more blocked, so it gets warmer. We get more greenhouse gases by increase of concentration of water vapor, and this again increases the greenhouse effect, so it makes it bigger than this 1 degree. It's a positive feedback amplification, and it's very important. And there's a second positive feedback process, self-amplifying, and that's the ice albedo. And this here is the idea of an artist. It's not a real photograph, yeah. How the Earth might have looked like in the ice ages. And you see here the North Pole region, it's all white because it's all covered, even North Europe and North America is covered by ice shields and snow. And that makes our planet much whiter. And white means it does absorb less energy from the sunshine. So a lot of sunshine, solar energy is directly reflected back into the space, and Earth gets colder. So that is again a positive feedback. If it's for the ice ages, if it gets colder, we get more snow, Earth gets whiter, and it absorbs less energy from the sun, and it gets even more colder. That's a self-amplifying. It also works the other way around. If it gets warmer due to our CO2 emissions, then we get less ice and snow, and Earth gets darker. And dark means it absorbs more solar energy and gets even hotter. So it's a self-amplifying or an amplifying feedback process. So these are the two main feedback processes, positive feedback processes, which convert this 1 degree from Professor William Happer to about 2 degrees from the IPCC. And it's even more than 2 degrees. I will show you in a minute. So the mistake or the error we have with this 1 degree is that only the direct response is calculated without the feedback processes. But that the feedback processes are really existing, we can prove, because since about 1 million years, our planet is in a cycle of ice ages, warmer times, ice ages, warmer times, ice ages, warmer times. Yeah, and we had, for a long time, we had no explanation why there are ice ages. And the last ice age, it ended about 10,000 years ago. So why did it end? And why did we had an ice age at all? And this can only be explained by these feedback processes, because the ice ages get triggered by very small changes of the orbit parameters of Earth on its orbit around the Sun. These are the Milankovitch oscillations. Well, that's a full lecture to explain that. But these Milankovitch oscillations, small things changing the orbit of Earth around the Sun, they change a little bit the radiation, Sun's radiation to the northern part of the planet. And these are only small changes, and you wouldn't be able to explain that there are ice ages and warm times, but only with these feedback processes. Then it's sufficient. So if the small changes of the Milankovitch oscillation get amplified by the positive feedback processes, then we are able to explain the many cycles of ice ages and warmer times in between. So the existence of ice ages is a proof that these feedback processes are really working. So we need them. And if we don't consider them, then we make a big mistake. So what does the IPCC tell us about the climate sensitivity? Actually, there are two. This is from two parts of the PDF from the assessment report number 6 here. And I think this is from the summary for policymakers. There are two climate sensitivities. One is the transient climate sensitivity, and the other one is the equilibrium climate sensitivity. Let's talk first about the transient climate sensitivity. And it means that we will double the concentration maybe in 2060, 2070, something like this, if we continue to emit CO2 as we do today. So, and then what will be then? In this very moment, we reach 560 parts per million. In this very moment, what will then be the global mean temperature in this moment? It will be about 2 degrees centigrade increase compared to the pre-industrial value. And we have here all kinds of different approaches to calculate or to estimate this temperature, from process understanding, instrumental record, and so on. And I refer her to all these crosses. These are the results of the different climate models. And of course, the climate models, they don't agree. All climate model comes, different ones come up with different results for the same thing. And though there we have an uncertainty range. And the middle is about 2 degrees, as you can see here, 2 degrees Celsius. But it ranges from 1.5 to about 3 degrees Celsius. So what the climate models tells us, and I believe that more or less, yes, is that we will have a warming in the case of 560 parts per million when we reach that in about 50 or 70 years or so of 2 degrees, but it could also be only 1.5, but it also could be 3 degrees Celsius. We don't know exactly. That is the transient climate equilibrium. Okay, and this is much more than what Professor William Happers tries to tell us. Yeah. And then there's, of course, another climate sensitivity, and this is the equilibrium climate sensitivity. Because once we reach 560 parts per million CO2 concentration and then stop emitting CO2, and maybe this just stays constant, let's assume that it stays constant, then the Earth system is still not in equilibrium because the oceans are too cold. They will get warmer with time. So the climate warming is delayed, and it will continue to get warmer even if we stop emitting CO2. And if we wait several hundred years, it will get much warmer than these 2 degrees here. And this is called equilibrium climate sensitivity. And this is this range here. It ranges from 1.5 up to 5.5 degrees Celsius. So the middle is something like 3.5 degrees Celsius warming at 560 parts per million. However, this equilibrium climate sensitivity is not relevant for us because it's several hundred years in the future. So, and in this very long time scale, the planet might have changed a lot, and also human civilization might have changed a lot. And I'm sure we will have no longer problems in 200, 300 years with CO2 emissions than we have other problems. So for us, relevant is a transient climate response. And we have to consider that we have 2 degrees or maybe a little bit more warming if we double the concentration. Yeah, and so I follow the analysis here from the IPCC, and I try to explain to you this is because of the positive feedback processes. Yeah, this is one point from the arguments of Professor Happers. And then we have a second point, and this is here, this statement. Today's 515 part per million CO2 level is near a record low, yeah, 515. It's a few years ago. It was 515 as it's this time. Today in 2024, we have 420 parts per million. Near a record low, not a dangerously a record high, because we have always these statements from politics and from the media. We never in the past had such a high CO2 emissions, CO2 concentration in the atmosphere like today. Yeah, but this always refers to the last 1 million year. If we say compared to the last 1 million year, this is correct, because during the last 1 million year, the level of CO2 was always below 300, yeah, and today we have 400 something. So it is the highest level, record high, within this 1 million year. And so Professor Happers did a kind of a trick, yeah, I think it's a trick, but it's correct, it's scientifically correct. He expanded the range of time to 600 million years, much longer time scale, back into the past of Earth. And this is a picture here. So what we have here is 0 means today. So this is 0 million years before present. So this is 1 million years, then 50 million years, 300 million years, 600 million years before present. And on this extremely long time scale, it's still a short time compared to the age of Earth. Earth is 4,600 million years old, so it's much older. So this is only the very end of the development of Earth, but still it's a huge amount of time, 600 million years. And the blue curve here, this is what scientists believe is the concentration of CO2. And it was most of the time, and here is Professor Happers, right, most of the time much higher than today. Yeah. So it's here, well, you see that this is 250 million years before, in this time regime here, between 250 and 0. Today we had something like 2,000 parts per million. And if we go further back in the past, we have 3,000, 4,000, or even 7,000 parts per million CO2 concentration. So indeed, on this very long time scale, it was much, much higher. There was a time in between here, between 350 and 270 million years before today. We had a low concentration. This was a terrible ice age, yeah, so we don't want to have that. But most of the time, especially during the last 250 million years, it was much higher CO2 concentration, and it was much warmer. And so this is an argument from Professor Happer. From Professor Happy, he says, well, it was not that bad for life. Indeed, it's true. During this 500 or 600 million years, life flourished. We had a huge development of life. Yeah, there was, for example, something like 150 or 200 million years ago, there were all these dinosaurs. And the Earth, the planet, has no ice caps. It was ice-free. And all over the planet, we had a tropical climate. It was warm and very wet. So a completely different Earth, yeah. And he says, yeah, it was very good for the life. This very hot planet, it was not so hot. It was not, well, the animals and the plants didn't die. It's just the opposite. They thrived, yeah. It was flourishing, the life, in this very hot climate all over the planet. However, and this is a point where I don't agree with Professor Happer. He concludes from this observation, it was much hotter, much higher CO2 concentration, and life flourished. So that means life would flourish again if we would have again this hot climate. And I don't agree with this conclusion, because how was a planet at this time, especially the last 250 million years? It was a very long period of tropical climate, but we had, as I said, no ice at the poles, but the sea level was 80 meters higher. About 80 meters higher. Though that would be bad, because the humans are living mostly in these flat areas closer to the coasts. Yeah, so we would lose this living space on the continents if the sea level would rise that much. And then we had a temperature, it was plus 8 degrees Celsius. This is plus 14 degrees Fahrenheit. So much hotter, plus 8 degrees Celsius here, at least this is what I learned in these 250 million years. And the climate was extremely wet because, as I explained, if it gets warmer, more water vapor comes out of the oceans, and that makes the climate extremely wet. So we get all kinds of heavy rainfall and floodings. Yeah, so it would be really a completely different planet. We would not die out. No, it's not that we die, but it would be difficult with the 8 or in the future maybe 10 or 12 billion people to live in this hot climate. So I think it's kind of extremely optimistic to tell the people, well, if it's getting so hot, it's not that bad. I think it's bad. It shouldn't become that hot as it was in the last 600 million years. But we are not going to die out. Yes, that's true. Okay, so it's a completely different planet. So that's one statement. He said CO2 concentration was much higher during the last 600 million years, and it was not bad for life at all. But I say it would be bad for today's humankind. Too hot. Okay, and then there's another statement, and he says this is this complicated picture here, and I refer now especially to the red curve here, and it's again on the last, 570 million years. It's a non-linear scale here. it starts at 4.6 billion years, 4,600 million years, and it goes until zero. This is today, 0 million years before today. And what we see here, the red curve, is the proposed, what the scientists think, the global average temperature. And what we learn from this curve here, it's from, actually here's the link, it's from Scottese. Professor Scottese made this nice, very simplified, it's very simple, but the real science is much more complicated. What we learn here from this picture is that the temperature never get above 25 degrees Celsius of the average temperature. So today we have this 15 or 16 degrees Celsius. So that would mean a warming of 9 to 10 degrees Celsius. So that would be kind of a maximum. So this work here suggests that there's a maximum temperature, 25 degrees Celsius. That means a tropical planet, but it's not getting hotter than that. And that means, well, 25 degrees Celsius, you can think about whether you will live on such a hot planet, but we are not going to die out. So it's the same message like the plot before, but referring not to the CO2 concentration, but to the temperature. And so the text in the paper from Professor Happers says 600 million years of CO2 and temperature data contradict the theory that high levels of CO2 will cause catastrophic global warming. He says it's not catastrophic, it's just the opposite. Life flourished, which is true. But again, as I would say, that would be very bad for humankind. But this is a science, yeah, it's true. But the real science is this here. This is what I use in my lectures. It's not such a very simplified plot or diagram from Professor Scottese. This is the real data here. What we see here, this is for my lecture, yeah. Well, of course, I'm sorry, it's a bit more complicated. I will not explain everything on this transparency here. But this is now from a science paper from 2020, so pretty new. And what we see here, the upper curve is the important one, is the isotopic ratio between for ocean sediments here for the O18. This is one of the stable isotopes of the oxygen atom. And this isotope ratio is a measure of the temperature. This is what the people believe. So it gives us an idea how the temperature developed in the past. And here we cover time between 65 million years ago until today. So this is the real curve, what we think what happened to the temperature. And there was an early Eocene climate optimum. It's about 55 million years ago. It was quite hot. And if we look to the temperature scale here on the very right, 0 means zero change between today with respect to today. So in the Eocene climate optimum, the hottest time, it was about 13 degrees hotter than today. Well, that would be quite a hot climate, yeah. But that was the case, at least to this data here, real measurements of the isotope ratio 55 million years ago. And then we had all the time cooling. The temperature dropped and dropped and dropped. Actually, in 2 steps. There was first here a steep step here about 35 million years ago, and it got cooler. It got colder at this time. And this is because of change of the positions of the continents on the surface of the Earth. The Antarctic, this is a continent at the South Pole, got very isolated at the very position at the South Pole, and now Antarctica, this continent, is kind of the refrigerator of the planet. Yeah, so this change in the positions of the continents made this drop in temperature, the dramatic top, and then East Antarctica get his first ice shields. Before that, the planet was ice-free, and then there was a second drop in temperature here when also West Antarctica gets covered with ice shield, and finally the North Pole here after 3.5 million years. This is here the last drop in temperature. Also freezed. It gets like today. Yeah, the North Pole is also ice covered. So this is what happened in the past, and indeed, it was much warmer if we go back in time. And the CO2 concentration, it's not plotted here, but it is probably has been much higher than today. And that is the real temperature change. And one could say, yeah, it was not bad for the life, but we are used to this climate, and we shouldn't go back to this climate, at least not too fast. We should have time, let's say a few thousand years, to adopt to this very hot climate if it comes back. But we will not hope that. Yeah. Okay, so that is real science. I wanted to show you these real measurements of the temperature. It's deduced the temperature in the past from isotope ratio measurements of the sediments in the ocean. Okay, and now this is a nice picture here. It shows you how Greenland might have looked like 3 million years ago. And this age was called late Pliocene. Yeah, Pliocene. They all have fancy names for these time intervals. 3 million years ago. It was much warmer. And yeah, it was a lovely island, yeah, with green fields. No, not fields. Well, of course, there were no humans, at least no farming and nothing. So we had forests and grassland, and the high mountains were covered with some ice. So it was really a lovely island at this time. And it's interesting to compare what we know about this, the status of Earth 3 million years ago. The ideas of the scientists are, well, we don't know exactly. That's a problem. There are always huge error bars. But the idea is it was about 3 degrees Celsius warmer at that time. And that meant that Greenland is no longer covered with ice shields. It's a green island, yeah? So total change. And the sea level was 15 meters higher. That would certainly be bad for us, yeah? With 3 degrees Celsius warming. And the CO2 concentration, well, big error bar, of course, but the average idea was it was maybe 400 ppm, like we have today. So, yeah, that could mean with this 400 parts per million, we are on the way to a warming of 3 degrees Celsius. Yeah, but it's not quite true, because 300 million years ago, the position of the continents were different. Especially, there was one important difference. And the connection between North and South America, it was not closed. So, and the Gulf Stream at that time, more than 3 million years ago, it went not to Northern Europe, but it went into the Pacific. So completely different pattern of ocean streams. Yeah, so they were different, and that causes a completely different climate. So it's not that simple that if we come up with 400 ppm, we will get a warming of 3 degrees Celsius like we had 3 million years ago, because we had different positions of the continents. Well, especially this Middle American isthmus, it was not closed; it was open for the ocean. Yeah, but yeah, well, it looks nice, yeah. But if Greenland loses his ice cover, we will have a sea level increase of 15 meters, and this is not exactly what we would like to have. Yeah, so that's the ideas of Professor William Happer, and I don't agree with the evaluation of him that it's not so bad. I think 3 degrees Celsius of climate warming would be too much for us, and I'm totally certain that it will not happen. We will find ways to avoid that, but we shouldn't say, oh, it's nice to get a little bit warmer. No, that is not exactly what we should hope. Okay, my conclusion. These are just 3 of these 4 arguments I picked out of this paper. There are some more things we could discuss, but then the video will take forever. So the transient climate sensitivity is approximately 2 degrees Celsius and not 1. CO2 concentration were much higher in the past. That's true. It was good for life, but wouldn't be so good for us. Yeah. In the past, temperatures were usually not above 25 degrees Celsius. That would be 10 degrees higher than today. That seems to be an upper limit. That's a good news. Yeah, so temperature is not going to infinity. There's an upper limit, and there's also a physical reason for that. I'm not going to explain, but it will not become as hot as on planet Venus, where we have 450 degrees Celsius. Yeah, there's a runaway greenhouse gas greenhouse effect. We won't get that. So the path of the Earth tells us there's an upper limit, 25 degrees, and that's the worst thing we have to deal with. But this certainly will not happen right now. Yeah, but this is good news. Yeah. That seems to be an upper limit. So we have an upper limit here. That's good. We won't burn up, yeah, but it would be a huge problem for humankind. Yes, of course, yeah. Climate models. Oh, this is the one I skipped. I didn't want to explain. That would take too long. But he also referred to the quality or the error bars of the climate models. Climate models tend to predict temperature increases that are too high, at least in the past. And I think they get better. They have gotten better today, but we need them. That's my opinion, and they will get better. We need the climate models, despite they are not real science, because we cannot do experiments to prove whether their predictions are correct or not. But we need them so that we get an idea what happens if we change this or that thing in our climate system. So the best thing we have, and we can only rely on the people who program these climate models, that they do their best to produce reliable data. Yeah, that's all. We can only hope that. Okay, so that's my conclusion, or my attempt to discuss the ideas of Professor Happer and Professor Linson in this paper I mentioned in the very beginning. So this was all be told in German, but I did my best to explain it to you. Yeah, thank you very much. This was my first attempt with an English video, and I'm sure if I make more of these English videos, probably my English will become more eloquent, more liquid, I hope. So this was it. Thank you very much. I have this homepage here. This is my speaker's homepage. So if you want to have booked me as a speaker, I can also tell you physics in English. Thank you, in German. Thank you very much.